So this question is asking to predict the product and then also to draw the mechanism for that transformation. When you look at the reagents right there, that's screaming Birch reduction. That's when you have solid sodium, methanol, and liquid ammonia. Okay, that's just screaming Birch reduction. We also have learned from the Birch reduction that any carbon on the benzene ring that's directly attached to an electron withdrawing group, then that carbon that I just circled right there will be reduced. Whereas a carbon on the benzene ring that's attached to an alkyl group or an electron donating group does not get reduced. Now, in my other videos, I explain why that is the case. But we are just going to talk about, just leave it at that. So knowing this about the electron withdrawing group and the electron donating groups, we can predict what our product is going to look like. So the electron donating group carbon is not going to be reduced, so that double bond stays there. Whereas the purple carbon is attached to an electron withdrawing group, so that is going to be reduced. So we're going to add a hydrogen there. So that means we're going to now move the double bond over there. Okay, so that's the Birch reduction product. Now, how do we go about showing that? Well, first thing is, I like to notice that I have 0 hydrogens in the purple carbon, and we have to add 1, okay? And then this carbon right there has 1 hydrogen coming off of it, but in the product, there's 2. And so I identify where those hydrogens are being added. And if those are the carbons that are adding hydrogens, then I know I have to get a lone pair on that carbon. Oops. I need to get a lone pair on this carbon and that carbon at some point of the reaction, because it's the lone pair that is going to be used to abstract a proton off of methanol. So let me demonstrate what I mean by that. So our first step in this mechanism is to keep things just easy to draw. I'm just going to go W for withdrawing group, D for donating group. Okay, so I don't want to draw that other 6-membered ring over and over again. We'll just draw the benzene ring. So with solid sodium in liquid ammonia, it basically has this electron that the sodium wants to get rid of. Okay, and so what's going to happen is that we're going to have this radical mechanism in which we're going to take 1 electron and stick it on that carbon that's attached to the electron withdrawing group, and then the other electron in that pi bond to that carbon. But the electron from the sodium is going to come and be placed right on that carbon that's directly attached to the electron withdrawing group. So we do that. So we have our W, and that stays there. So what has happened now? We have a radical there, and then a lone pair right there. Now recall at the beginning of the video, I said that we want to have a lone pair on that carbon, which is that carbon, because we need that lone pair to come and abstract a proton off of methanol. So if we do our next step here and show methanol like this, now we have that lone pair that can come and grab that proton. And so that is going to give us a product like this. The electron withdrawing group, the hydrogen that was added, deuterium still there, that double bond still there, that double bond still there, and then we would still have our radical right there. We notice in our product that our hydrogens are right there. Okay. So what do we want to do? Well, we know that we want to have a lone pair on that carbon so we can add another hydrogen. So how do we add that other hydrogen? Okay. Well, look at this. We can draw a resonance structure. So let's go like this. Draw ourselves a resonance structure in which we can take this one electron and put the double bond there. And then this electron right here, put, oh, wrong arrow, has to be a fishhook arrow, like that. When we look at that resonance structure, electron withdrawing group, the hydrogen's still there, D, there. We would have a double bond there now, and then a radical. And so the next step would have to be we would take another sodium atom, say it's going to love to just donate an electron. And when it donates that electron right there, we are going to get our anion. So we're going to have the lone pair. That's going to be negatively charged. We still have the pi bond right there. And now we can use that to abstract the proton off of methanol. And pay attention to my curved arrows. Sometimes I use fishhook arrows, sometimes I do not. And they mean different things. Okay, so we'll take this and go down here. And so now we added our second hydrogen. And I don't need to draw in those hydrogens anymore. Just like that. Which translates into our final product. That looks like this. And so that's the mechanism. And obviously the methanol right here that's used here, it would still be the methoxide floating around. And our first time that we did methanol, it would look like this over here as well. Okay. And then what does the sodium look like after it donates its electron? We'll just have a sodium plus and a sodium plus. Okay, just floating around. As it's just now, once it's the cation, it's just going to be a spectator ion. But that is the mechanism for how to do that reaction.